Two ice giants sit at the outer edge of our solar system, spinning on axes that shouldn't, by almost any conventional model of how planets form, be tilted the way they are. One of them, Uranus, doesn't just lean, it lies almost completely on its side, spinning like a rolling ball while every other planet in the solar system spins closer to upright, like a top. For decades, the leading explanation was a violent one. Something enormous slammed into it billions of years ago and knocked it over for good. That explanation has real evidence behind it, but it's never fully closed the case. And in the search for what else might explain Uranus's strange, extreme tilt, one persistent thread of research keeps pointing toward the same tantalizing possibility. A planet we've never actually seen, tugging on Uranus from an orbit so distant that confirming its existence directly remains, for now, just out of reach. This is the story of why Uranus and Neptune are tilted the way they are, what scientists have proposed to explain it over the past 2 decades, and why one specific, still unconfirmed hypothesis involving a hidden 9th planet keeps surfacing as a genuine, mathematically serious possibility, rather than speculation dressed up for a headline. To understand why this particular puzzle has occupied planetary scientists for so long, you first need to understand exactly how strange Uranus's tilt actually is, and why it stands out so clearly against every other planet in the solar system. Every planet in our solar system spins on an axis, the way Earth spins on its axis, once every 24 hours. That axis is rarely perfectly perpendicular to the plane in which the planet orbits the Sun. Earth's own axis, for instance, is tilted by about 23.5 degrees, which is the entire reason we experience seasons. Astronomers call this tilt a planet's obliquity, and across the solar system, most planets have relatively modest obliquities, generally under 30 degrees. Jupiter's axial tilt is a mere 3 degrees, barely noticeable. Saturn's is about 27 degrees, similar to Earth's. Neptune sits at roughly 28 degrees, again broadly comparable to Earth and Saturn. Uranus is the outlier, and it isn't a small deviation from the pattern. Its spin axis is tilted by approximately 98 degrees relative to its orbital plane, which means Uranus doesn't just have a pronounced seasonal tilt the way Earth does. It's tipped over so far that it's spinning almost entirely on its side, with its poles pointing roughly toward where other planets have their equators. As one detailed review of the problem, published by researcher Tiger Liu at Yale University, put it plainly, conservation of angular momentum in the early solar system would naively suggest that planetary axial tilts should generally be close to zero, since planets are thought to form from a relatively flat, rotating disk of gas and dust, which should, in principle, leave newly formed planets spinning in roughly the same orientation as that disk. In reality, we see a wide range of obliquities across the solar system's planets, and Uranus represents by far the most extreme case of that pattern breaking down. For decades, the most widely accepted explanation for Uranus's extreme tilt has involved violence, a colossal collision occurring near the end of the solar system's early formation period, when large planetesimals, primitive planet-sized building blocks, were still slamming into the young giant planets as the solar system settled into something closer to its current configuration. According to this model, discussed in detail across multiple peer-reviewed studies, including work by researchers Morbidelli, Isidoro, and Salmon, and Canup, a body somewhere between roughly 1 and 3 times the mass of Earth struck the young Uranus with enough force to physically knock its spin axis over to its current extreme angle, all in a single catastrophic event. In this general framework, both Uranus and Neptune are thought to have acquired essentially random spin axis orientations through this kind of impact process, in contrast to Jupiter and Saturn, whose more massive, more rapid runaway gas accretion during formation is believed to have kept their own obliquities driven closer toward zero. That giant impact explanation has real, credible physical support behind it, and it remains even today the most widely cited single explanation for why Uranus ended up tilted the way it did. But it has a significant, persistent weakness that researchers have continued grappling with for years. It doesn't cleanly account for several other specific features of Uranus's current satellite system. Uranus's major moons orbit the planet in a neat, orderly configuration that lines up closely with the planet's current tilted equatorial plane, rather than showing the kind of scattered, chaotic orbital arrangement you might expect to result from a single, violent, off-axis collision powerful enough to physically flip an entire planet onto its side. If a massive impactor really did knock Uranus over in one dramatic event, explaining why its moons ended up in such a clean, well-ordered arrangement afterward, rather than a scattered mess, has proven considerably more difficult than explaining the tilt itself. That gap in the giant impact model is precisely why researchers have spent the past 2 decades developing and testing alternative explanations, ones that don't rely on a single violent collision at all. And it's within these alternative models that the possibility of a hidden, undiscovered planet keeps resurfacing as a serious, if still unconfirmed, candidate. One major category of alternative explanation involves something called spin-orbit resonance, a phenomenon considerably less dramatic than a planetary collision, but potentially just as capable of producing an extreme tilt over a much longer stretch of time. Here's the basic idea, described across several published studies, including work by Bouet and Laskar, Quillen and colleagues, and more recent work by Milholland and Badigan, and separately by Rogosinski and Hamilton. Every planet's spin axis naturally wobbles very slowly over time, tracing out a slow circle in space, a phenomenon called precession, similar to the way a spinning top's axis slowly traces a cone shape as it spins. Independently, every planet's orbit also experiences its own slow, gradual changes in orientation over time, driven by the combined gravitational influence of the other planets in the solar system. Under specific conditions, if a planet's spin axis precession rate happens to fall into a mathematical resonance with certain frequencies arising from its orbital dynamics, the two motions can begin reinforcing each other, gradually amplifying the planet's tilt over a very long period of time, rather than requiring a single violent event to produce the same result all at once. Researchers have shown mathematically that, under the right resonance conditions, this kind of gradual process is capable of pushing a planet's obliquity from something close to zero all the way up past 90 degrees, and in certain specific scenarios, even further still. The specific challenge with applying this resonance model directly to Uranus, as Liu's review lays out clearly, is that Uranus's spin axis currently precesses far too slowly to match up with any of the relevant orbital frequencies present in the solar system as it exists today. That mismatch doesn't rule the resonance model out entirely, but it does mean that if Uranus's tilt really was produced this way, the resonance condition responsible for it would have needed to exist under different circumstances than what we observe now, most plausibly sometime much earlier in the solar system's history, when the outer planets were still migrating through the solar system to reach their current orbital positions, a period when the relevant orbital frequencies would have been considerably different than they are today. This is precisely where the missing planet hypothesis enters the picture directly, and it's worth being clear that this isn't idle speculation invented for the sake of a compelling story. It connects to one of the most actively studied, still unresolved questions in modern planetary science: the potential existence of a large, distant, as yet undiscovered planet in the outer reaches of our solar system, generally referred to by researchers as Planet 9. The Planet 9 hypothesis originated separately from the Uranus tilt puzzle, first proposed based on unusual clustering patterns observed in the orbits of a number of small, distant icy bodies out beyond Neptune. Patterns that several researchers have argued are difficult to explain unless a large, unseen planet, several times the mass of Earth, exists somewhere in a very distant, elongated orbit far beyond the currently known planets. That hypothesis remains genuinely unconfirmed. No telescope has yet directly observed Planet 9, and there remains real, ongoing scientific debate about whether the orbital patterns used to argue for its existence might eventually be explained through other means entirely, without requiring an additional planet at all. What connects that separate, ongoing debate to the specific question of Uranus's tilt is a mathematical possibility explored directly in research by Liu and collaborators at Yale. As Liu's own summary of the work describes it, Uranus's spin axis currently precesses too slowly to match any known resonance frequency in the solar system as it exists today, but Planet 9, if it exists, is believed to have originally formed much closer to the Sun and to have gradually migrated outward to its current, extremely distant orbit over a long period of time. As a hypothetical Planet 9 migrated outward through the solar system, its gravitational influence on Uranus's orbital node, one of the key factors determining exactly which resonance frequencies are available to interact with Uranus's spin axis, would have gradually changed as well, potentially opening up a temporary pathway for Uranus to become captured into precisely the kind of resonance condition needed to gradually tilt its spin axis over time without requiring any single violent impact at all. Liu and colleagues performed detailed simulations modeling exactly this scenario, tracking how Uranus's spin axis might respond as a hypothetical Planet 9 slowly migrated outward, testing whether this specific mechanism could plausibly account for Uranus's current extreme 98-degree tilt. It's important to be precise and appropriately cautious about exactly what this research does and doesn't establish. This work demonstrates that a distant, undiscovered planet could, mathematically and physically, provide a viable mechanism for tilting Uranus gradually over time through a well-understood resonance process without requiring the kind of violent, singular collision that leaves harder-to-explain traces in Uranus's orderly satellite system. It does not, on its own, prove that Planet 9 exists, nor does it prove that this specific mechanism is what actually happened to Uranus, as opposed to the giant impact scenario, or some combination of both processes acting together over time. What it does represent is a genuine, mathematically serious research thread, connecting two of the more significant open questions in modern planetary science: the true cause of Uranus's extreme tilt and the potential existence of a large, hidden planet in the distant outer solar system, in a way that offers a coherent, testable explanation for both puzzles simultaneously, should further evidence eventually confirm Planet 9's existence directly. While Uranus's tilt has remained genuinely unresolved, ongoing research into Neptune's considerably smaller, though still notable, 28-degree tilt has recently produced what appears to be real, meaningful progress, and it's worth walking through that story as well, both because it's genuinely interesting in its own right, and because it illustrates just how differently two seemingly similar planetary puzzles can ultimately be resolved. Neptune's tilt has generally been considered a somewhat easier problem to explain than Uranus's far more extreme case, since 28 degrees, while still notable, falls much closer to the range seen across the rest of the solar system's planets. Several explanations had already been proposed over the years, including the possibility of an early tilt originating during the planet's initial formation, or a resonance crossing event occurring later, during the broader migration of the outer planets, similar in spirit to the mechanisms proposed for Uranus. In early 2026, new published research offered a specific, detailed alternative explanation centered not on any large impactor or migrating hypothetical planet, but on Neptune's own largest moon, Triton. According to this research, Triton's slow, gradual tidal evolution around Neptune, the long, ongoing process by which a moon's orbit slowly changes shape and orientation over enormous stretches of time due to gravitational interactions with its host planet, could plausibly account for Neptune's entire current tilt, without requiring any external collision or additional hidden planet at all. Running detailed simulations of Triton's long-term orbital evolution, the researcher behind this work found that in roughly 1 out of every 3 simulated scenarios, Neptune's tilt reached over 20 degrees purely as a natural consequence of Triton's gradual tidal migration. And in some specific simulation runs, Triton's gravitational influence proved strong enough to push Neptune's tilt beyond 50 degrees entirely. Crucially, the specific value these simulations most commonly converge toward, a natural resting point produced by Triton's long, slow orbital journey toward its current position, closely matched Neptune's actual observed tilt of 28 degrees. That finding carries a broader significance well beyond simply explaining one planet's tilt. As the research itself points out directly, if this specific mechanism holds up under further scrutiny, it means we don't necessarily need any catastrophic, singular event, whether a giant impact or a passing hidden planet, to explain why an ice giant like Neptune ended up tilted the way it did. A slow, ordinary, entirely nonviolent process, the gradual tidal dance between a planet and its largest moon playing out over vast stretches of time, may be entirely sufficient on its own. That has real implications extending beyond our own solar system as well, since it suggests that similar, non-catastrophic tilting processes could plausibly be common among ice giant planets discovered around other stars throughout the galaxy, many of which are now known to possess large moons of their own, without necessarily requiring the same kind of violent formation history that's traditionally been assumed necessary to produce a significant planetary tilt. Sitting these two separate lines of research side by side, the Triton-driven explanation for Neptune's more moderate tilt, and the still unresolved combination of giant impact and resonance-based explanations, including the Planet 9 connection, for Uranus's far more extreme case, offers a genuinely useful illustration of how differently two superficially similar planetary puzzles can ultimately be resolved. Neptune's tilt appears to be steadily converging toward a well-supported, relatively mundane explanation, involving nothing more exotic than its own largest moon's ordinary long-term orbital evolution. Uranus's far more extreme tilt remains considerably more resistant to any single fully satisfying explanation, continuing to require some combination of violent early collision and longer-term resonance effects, quite possibly including the gravitational influence of a planet we haven't yet directly confirmed exists at all. It's worth stepping back and being fully honest about where the overall scientific consensus currently stands on this entire question, since that honesty matters more than any single dramatic possibility contained within it. The leading explanation for Uranus's extreme tilt remains a massive early collision with a large planetesimal, a scenario with genuine, credible supporting evidence, even though it still struggles to fully explain the clean, orderly configuration of Uranus's current satellite system. The spin-orbit resonance models, including the specific version involving a migrating hypothetical Planet 9, represent a genuinely serious, mathematically rigorous area of ongoing research, one actively being pursued by working planetary scientists using detailed numerical simulations rather than idle speculation. But Planet 9 itself remains fundamentally unconfirmed. No telescope has yet captured a direct image of it, and there remains real, legitimate scientific debate about whether the broader body of evidence generally cited in support of its existence might eventually be explained through other means entirely. What connects all of this together, and what makes it genuinely worth paying attention to, regardless of how any individual piece of the puzzle is eventually resolved, is the underlying scientific approach itself. Researchers studying Uranus's extreme tilt aren't simply speculating freely about whatever explanation sounds most compelling. They're building detailed mathematical models, testing specific, quantifiable predictions against Uranus's actual observed properties. Its exact tilt angle, the detailed configuration of its satellite system, its current spin axis, precession rate, and steadily working to determine which proposed mechanism, or which combination of mechanisms, best accounts for everything we can currently observe and measure about this genuinely unusual planet. Confirming or ruling out the specific role a hidden ninth planet may have played in tilting Uranus onto its side will likely require exactly the kind of evidence that's already being actively pursued by multiple survey telescopes and research teams around the world. Either a direct detection of Planet 9 itself, definitively confirming its existence and allowing researchers to precisely measure its mass, orbit, and migration history, or, alternatively, a sufficiently refined understanding of the alternative explanations, like the resonance and impact-based models discussed here, robust enough to fully account for Uranus's extreme tilt without requiring any additional hidden planet at all. Until one of those two outcomes arrives, the question of exactly what tilted Uranus onto its side, whether a single ancient collision, a longer resonance process involving a planet we haven't yet found, some combination of both, or something else entirely, remains one of the genuinely open, actively researched puzzles in modern planetary science. There's something worth appreciating in the fact that this question remains open at all, more than half a century after Voyager 2 first gave humanity a close, detailed look at Uranus's extreme, sideways tilt during its historic flyby in January of 1986. It would be easy to assume that a solar system explored, mapped, and photographed in detail across 4 decades of robotic missions has, by now, given up nearly all of its genuine mysteries. Uranus's tilt is a clear, direct reminder that isn't the case. A planet sitting nearly 2 billion miles from the Sun, tipped over so far it spins almost entirely on its side, continues to resist a fully satisfying explanation. And one of the most actively pursued paths toward finally solving that mystery runs directly through the search for another planet entirely. One that, as of today, nobody has ever actually seen. If you want to follow how this search develops, both for Planet 9 itself and for the final answer to what really tilted Uranus onto its side, that story is still very much being written by researchers actively working on it right now. Subscribe if you'd like to keep following where it goes.